Okay, okay. So here we go. Today what we are going to talk about as computational chemistry using software, the quantum mechanics, the science behind. So I've chosen this topic just to have an understanding of what goes on behind the formalism of the software. Right. So computational chemistry, if talk about, is a discipline which deals with the modeling and the computer simulation of systems used such as biomolecules, polymers, drugs, inorganic and organic molecules. It uses methods of theoretical chemistry incorporated into different computer programs, efficient computer programs to calculate the structures and properties of molecules under the domain of molecular modeling. And the computational chemistry also brings about modeling of processes or experimentations, and which is known as molecular simulation. So I think now we can make a distinction between the simulations and molecular modeling. Now, when we talk about molecular modeling, then the question arises, why molecular modeling? So the simple answer to this question can be achieved by saying that modeling and calculations can give us an insight which is beyond experiments in many cases. For example, uh, if we want to understand a chemical reaction, we need to know the transition state structure for the reaction. Transition states are difficult to study by virtue of experiments. So instead, their structure can be calculated and analyzed using this molecular modeling. So in a way, we can say this gives us an insight beyond experiments in many cases. Now, modeling and experiments, I do believe that they are best done in conjunction. Modeling helps us to interpret experiments. In contrast, we can say experiments test computer models. So there, this has been a, we can say that modeling and experimentation are best done in conjunction. Right. So which are the methods for doing this molecular modeling? There are two broad, this we can classify in two broad terms called molecular mechanics and quantum mechanics, which will come over to this molecular mechanics. Let us now start first of all with quantum mechanical methods. In quantum mechanical methods, basically the emphasis is on solution of Schrodinger equation, as we all know. Now, in order to obtain the wave function and psi, that is called, which is called the storehouse of information. So basically emphasis is also on extracting values of desired observable properties of system at hand. There are two types of Schrodinger equation we have. One is time dependent and one is time independent. The time independent Schrodinger equation is useful in predicting equilibrium geometries, structures of the chemical species, which is under study. Whereas time dependent systems, where we can make spectroscopic calculations. So let us now have a look at independent Schrodinger equation. This is just for a one electron problem, hydrogen atom. Simply to say, we all know that this has mainly the kinetic energy terms corresponding to the nuclei, the kinetic energy term corresponding to the electron, and the potential energy term mainly in terms of interaction between electron and nuclear charge. So I think somewhere there has been lines appearing on the screen. Anyway, so here, according to Born-Oppenheimer approximation, we all know that nucleus being assumed at rest. So therefore, we end up in having this Hamiltonian having only electronic terms. So it's called Schrodinger, electronic Schrodinger equation there. Then if we talk about helium atom, you see, this is the hydrogen atom which was exactly soluble. That is exactly solved through quantum mechanical methods that we have seen. Now coming over to helium atom, here we have two electron problem and a nucleus there. So in addition to kinetic energy term corresponding to nucleus, kinetic energy term corresponding to two different electrons, then we have nuclear electron interaction terms corresponding to both the electrons. Here one more term comes, that is electron-electron repulsion term.
Dr.
Now, hello.
Dr. Amit, Dr. Anjana Sarkar is there in the waiting room. Now that you are the host, can you please admit her?
Okay, sir.
Sorry to disturb you in the middle.
It's all right. It's all right. Let me check. Anjana madam was there, allowed earlier, I think. She's
Was there.
not,
She went out because of that audio problem, and now she's trying to join with the phone.
at the moment not there. At the moment not there. Yeah, she is there, right.
So just admit her.
Yeah, I have allowed her to join, right. Okay. 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 All right. All right, so here a new term called electron-electron repulsion terms which comes. If we just ignore this term for a moment now, we can see this problem just to be a sum of two hydrogen atom kind of problem. But because of this introduction of electron-electron repulsion term, it becomes almost impossible for solution, having an exact solution of this problem. So we look for approximate methods for solution. We shall talk about them a little later. All right. So slides are not moving. Okay. Waiting room disturbs continuously. Is the slide visible? It's not moving.
Yeah, slide is available, sir.
Actually, because of this waiting room pop-up, this does not move. Okay. All right. So basically, when we talk about this, beyond this helium atom, as we can see, only exact solution we could achieve for hydrogen atom when we go to helium atom. Because of this electron-electron repulsion term, the solution, it is difficult to achieve that solution. Now, beyond that, if we look at, let's say, hydrogen molecule, then there are about 7 different kind of terms, and a total of about 10 terms in the Hamiltonian do appear. So if we look at in that sense, I mean, the terms, because of as the number of atoms, the electrons do increase, the number of terms to be solved for in the Hamiltonian rise exponentially. Right. So as a general, if we can say that how many number of terms would be there for an electron and nucleus system? If suppose n is the number of nucleus and e is to be the number of electrons, then the total number of Hamiltonian terms can be estimated as n plus e times n plus e plus 1 divided by 2. So here we can look at the bifurcation as well. The bifurcation suggests us that because there are n electrons and n electrons and e number of electrons and n number of nucleus. So in that situation, then in that molecular picture, we will have n plus e kinetic energy terms, and VEN, that is electron nuclear attraction terms, that will be Ne in number. The nuclear repulsion terms n into n minus 1 divided by 2 in number, and E into E minus 1 divided by 2 as the electron repulsion terms. So this is just the bifurcation what we get as the number of terms in the Hamiltonian we get for a multi-electron, multi-nucleus system. So having said this, now the point is, we will just see if we go to benzene and small molecules like water, carbon dioxide, and ultimately to benzene, we will see that these terms which appear in Hamiltonian would just rise to 1400 plus terms for benzene. So what I wish to conclude from this observation is that the number of terms which do appear in the Hamiltonian, they do rise exponentially. Now you can see as they appear in this table. So 3 terms for hydrogen atom, the electronic terms I'm talking about, and this in benzene it turns out to be 1485. Now it is time to understand the different theoretical methods for solution of Schrodinger equation. As I said, the exact solution cannot be achieved, so it's only the approximate solution which we can get. So which are the different methods for this solution of Schrodinger equation? These methods have been, as you can say, is been classified as ab initio method. This ab initio method, we should talk about these methods in little brief about these methods. Then we have density functional theory and modified ab initio methods like MPN, molar pressure calculation, configuration interaction, and couple cluster calculations to it. Beyond that, we also have semi-empirical methods, and then finally we have beyond quantum mechanic calculation, that is molecular mechanics calculation. So these are the broad methods which do appear here in quantum mechanical calculations. So let us talk about the ab initio method, its main feature. Now, among the ab initio method, when we ab initio calculations, this name is given to computations which are derived directly from theoretical principles, such as the Schrodinger equation with no inclusion of experimental data. So right from it means once an approximate wave function is defined, no more further approximation. So it's first principles. The approximation made are usually mathematical approximations, such as using a simple functional form of a function or getting an approximate solution to the differential equation. So these are the two broad approximations. So let us talk about the primary approximation over here, which here is called the central field approximation. See, this method does not include any Coulombic electron-electron repulsion in the calculation. However, its net effect is included in the calculation by assuming that for a particular electron, each of the other electrons in the system is smeared out into a charge cloud whose interaction is calculated with each other, with each electron. So the reality is electrons, in fact, the reality is each electron repel one another and correlate their motion to avoid being close together. So this phenomenon is called electron correlation. That is, that each electron repel one another and correlate their motion to avoid being close together. So this phenomenon is called electron correlation. So it can be concluded that the Hartree-Fock wave function neglects the instantaneous correlations in the motion of the electrons. And this is a variational calculation also, which means it uses variation method to solve for the Schrodinger equation. Now, the fact is that the approximate energies, it means so calculated, are all equal to or greater than the exact energy. Now, because of the central field approximation, which I have just conveyed, according to that, the energies, as a result of that, the energies from Hartree-Fock calculations are always found to be greater than the exact energy and tend to a limiting value called the Hartree-Fock limit. So it means we get an overestimation to the exact value through this method called Hartree-Fock. Right. So the second approximation here in Hartree-Fock calculations is that the wave function must be described by some functional form, which is only known exactly for a few one electron systems like hydrogen atom, hydrogenic orbitals. So the functions used most often are linear combinations of Slater type orbitals or Gaussian type orbitals there also. So the exact set of basis functions used is often specified as abbreviated as such as STO3G or 631G, etc. because of this, also it further leads to overestimation of, because the wave functions is, it is using only those functional wave functions for one electron systems, so which may not replicate the exact system in a multi-electron nuclear system. So on these two counts, that is the central field approximation and using this one electron wave function, what we have is, when we solve for the Schrodinger equation using this ab initio-Hartree-Fock method, what we get is the overestimation of the electronic energies. This is the problem we get over here. So now in order to, so it means this all comes from because of these two counts. So we need to standardize the wave function, and then we need to account for the electron correlation also, which the central field approximation introduces. In order to account for that, we have several different methods called Moeller-Preset perturbation theory method, then generalized valence bond method, then multi-configuration self-consistent field method, configuration interaction, and coupled cluster theory. So basically, we have modified Hartree-Fock methods that account for this electron correlation. Most of these computations begin with a Hartree-Fock calculation and followed by further corrections for the explicit electron-electron repulsion, referred to as correlation corrections. So some of these methods which I have just listed here, so as a group, these methods are referred to as correlated calculations. So although these are the methods which bring good results, very good results, just they eliminate that overestimation of electronic energies. And these methods, however, require a linear combination of thousands or even millions of configuration functions to give an accurate representation of the wave function. And therefore, these methods are very, very time consuming and hence raise computation time and cost exponentially. So the idea is that Hartree-Fock, with the Hartree-Fock method, that it gives us overestimation to the electronic energies. When we introduce electron correlation studies, if using these methods, we get good results. But the point is, the calculation cost and computation time increases exponentially. So this is the drawback over here. Well, we now have different ab initio type of calculation. So in this calculation called density functional theory, this is an alternative ab initio method, we can say, that is density functional theory. And the Walter Kohn introduced this theory and got Nobel Prize in 1998 as well, jointly with John Pople, which we will talk about him also. So here in this theory, the total energy is expressed in terms of the total density rather than the wave function. It means now the wave function would be just representing the function of the density. So it means function of a function. And so function of a functional is called functional, and hence this theory is known as density functional theory. So in this type of calculation, there is an approximate Hamiltonian based on the estimation of the electron density, and an approximate expression for the total electron density as well. So it has been observed that DFT calculations give reasonably very good result at a computational cost nearing the conventional Hartree-Fock calculations. So this is the result, that this method has become the primary choice nowadays of people working in the area of computational chemistry. So because this try to give you better results at a even lesser cost, I mean cost comparable to the conventional Hartree-Fock method. All right, so now we can once again have a revisit to the ab initio method. The favorable aspect of ab initio method is that they eventually converge to exact solution once all the approximations that are made sufficiently small in magnitude. That means electron correlation also is being taken into account. The unfavorable aspect of ab initio calculations is that they are expensive. These methods often take enormous amount of computation, CPU time, memory, disk space, and therefore the Hartree-Fock method, you can say, scales as n raised to the power 4, which means where n is the number of basis functions. So a calculation will be twice as big as it takes 16 times longer to complete if we raise the number of particles present in this number of basis set functions in the linear combination. So correlated calculations often scale much worse than this, even worse than this. So in practice, extremely accurate solutions are obtainable only when the molecules consist half a dozen electrons or less. This is a general experience. So in general, we can say ab initio calculations give very good quantitative results when electron correlation is taken into account, can give increasingly accurate quantitative results as these molecules in question become smaller. So here we have to, look for a balance. What is the size of our molecule? What are the number of electrons systems which are being present in our system to be studied? So here we make a different call. What is the parameters to be studied? Or depending on all these factors, we will take a call which theory is to be chosen, either ab initio or with electron correlation, the density functional theory, and so on. Right. Now there is another set of calculations called semi-empirical calculations. What is that? Let us have a look at this semi-empirical calculations. Well, the semi-empirical calculations are set up with the same general structure as a Hartree-Fock calculation. That means a wave function, the Hamiltonian, so on. So, but within this framework, certain pieces of information such as two electron integrals, means electron-electron repulsion terms which we are talking about, are approximated or completely omitted. Now, in order to correct for the errors introduced by omitting the part of the calculation, the method is parameterized by a curve fitting in a few parameters or numbers in order to avoid the best possible agreement, in order to arrive at the best possible agreement with the experimental data. So it means we would take experimental data of similar molecules like bond angles, bond lengths, etc. into account over here, and we will use those parameters to parameterize in this method in order to account for omitting of the electron-electron repulsion. Right. So merit of the semi-empirical calculations is that they are much faster. You see, the computation time you will be just a small fraction of the computation time required for a Hartree-Fock calculations. So they are much faster than the ab initio calculations. But the demerit of these calculation is that the results can be slightly defective. How the defects is produced is that if the molecule under study is computed is similar to the molecules in the database used for parameterization of the method, then the results would be very good. But if the molecule being computed is significantly different from anything in the parameterization set, then of course the answer will be very, very poor. The results will be very, very poor. So basically, we also further need to take a call. Which kind of calculations, whether semi-empirical, the ab initio, density functional theory, or ab initio calculations with the electron correlation, which method we should look for. So we need to take a call depending upon the what kind of parameter we want to study, what is the study at hand of a chemical system. Right. If we talk about molecular mechanics, in molecular mechanics, basically comes to the saving part if we have to deal with very big systems. See, if a molecule is too big to be effectively used as to even look for a semi-empirical calculations like DNA molecule, DNA, proteins, if you want to talk about them, even it would be very difficult for us to look for the semi-empirical calculations about such large molecules. So this molecular mechanics calculation comes to rescue in that. So it is still possible to model this behavior of the behavior of such big molecules. So by totally avoiding quantum mechanics in it. The method here, molecular mechanics, referred to as molecular mechanics where the atoms in a molecule is considered like a ball which are connected with other atoms by something called springs. So ball and spring model, we can say, which represents basically the model for this molecular mechanics calculations. Right, here what one do is one sets up a simple algebraic expression for total energy of a compound with no necessity to compute a wave function or total electron density. The energy expression consists of simple classical equations such as harmonic oscillator equation, if you look at, and in order to describe energy associated with bond stretching, bending, rotation, and intermolecular forces such as van der Waals interactions and hydrogen bonding. All of the constants in these equations which we write must be obtained from experimental data also. Or if not available, then we can look for some similar ab initio calculations data on similar kind of structures. Right. In a molecular mechanics method, the database of compounds that are used to parameterize the method, a set of parameters and functions, is called a force field. So force field is very crucial to the success of this molecular mechanics method or calculations. The molecular mechanics method may be parameterized against a specific class of molecules such as proteins, as I said, big organic molecules, organometallic compounds, etc. So molecular mechanics, it means allows us the modeling of very large molecules by avoiding quantum mechanical electronic interactions. So that is helpful in finding interactions for molecules such as proteins and segments of DNA. So therefore, it basically is a, you can say, is a tool of computation biochemists. Right. And even we will see shortly, once we do make a particular geometry, input geometry of a molecule input to the software, we have an option to do first molecular mechanical structure obtained, and which can be given as an input to the program to get the semi-empirical ab initio DFT or other quantum mechanical calculations. Right. Having described these molecular modeling methods in just briefs, it is worth to mention now about a man called John Pople, who was a British scientist who shared a Nobel Prize, as I did tell you, in 1998 with Walter Cohen. He was awarded this Nobel Prize for developing computational methods in 1970s. So basically, thereby making it possible that the theoretical study of molecules, because you could see that the number of Hamiltonian terms rise exponentially. Even for a benzene molecule, we could see how many terms and how many how many integrals we will have to solve for. So if we go by doing it with hand and on a piece of paper, it would be almost impossible. So here he is the man, because when the advent of computers occurred, so he was the man who made a formalism actually for computational calculations for molecules, where a computer is fed with particulars of a molecule or a chemical reaction, and the output is a description of the properties of that molecule or how a chemical reaction may take place. So the result is often used to illustrate or explain the results of different kinds of experiments. Right. So now let us see what are the outcomes of molecular modeling. We get geometry optimizations. That means minimized, optimized geometry, which we will get to see shortly in the illustration of the software itself, how we to get that. Then molecular energies, structures, then energies and structures for transition states. We get, as I mentioned earlier, bond energies, reaction energies, and all thermodynamic properties. Molecular orbitals we get, then multiple moments, atomic charges, spectroscopic data. Then we can model excited states also here. So a variety of calculations we can get, and the outcome is just sufficient for us for description of chemical system at hand. Right. So thus, in order to do molecular modeling studies and for visualization of the outcome of results of such studies, we need computer program, as we have learned. So which when we integrate in the form of a convenient user interface, that user interface can be in terms of data interface or graphical mode, then such program take the shape of a software package. So what with this discussion of theoretical methods in the background, today we will be discussing about the usage of two such software packages that are absolutely user friendly, and these are namely the Spartan 18 and Odyssey software. It is worthwhile to mention over here that Spartan 18 is a research tool, is a research-based software, talks about hardcore research problems to be solved on this Spartan 18. Whereas if we talk about Odyssey software, this software helps us to, with the help of various tutorials to it, helps us to analyze the chemical discussion of a chemistry problem within the class. So therefore we can say Odyssey software is a much enhanced tool which we cannot find nowhere else, which helps us to enhance the classroom experience of a student. We will see shortly that how we can understand the concepts of chemistry through visualizations this Odyssey software brings about to take the learner's experience to the next level. And of course, Spartan 18 is a much enhanced software which comes for the calculations for research problems. So these are two entirely different softwares for different purpose. Fortunately, we are grateful that today we have with us the developer of the software himself with us. So I do think that we will get to hear much about the software, how it helps us in analyzing chemistry problem, doing research problems uh, from him itself. So I would like that uh, uh, now Dr. Jargan himself just illustrates the software, but before that I pass it on the mic to Dr. Navneet Manav, who can introduce Dr. Jargan and who can then start with this presentation. Thank you so much. And if you have some query, you can address to me. Yeah.
Dr. Amit, please make Dr. Jargan the host.
All right, sir. All right.
Do that. Go to Dr. Jargan's picture.
Okay, I just go to that.
With 3 dots, just make him the host.
All right.
Dr. Jargan,
yes.
Yatendra will be there in the waiting room. Once you become the host, you will find Yatendra there in the waiting room. Just get him in.
Dr. Amit,
Sir,
still
yes.
the host though.
I just do that, sir.
Okay.
Let's wait for a moment.
So if Dr. Yatendra is not there, so we can take the question compilation after both the speakers, I guess.
All right, all right,
Right.
all right.
So dear participants, if you have any question, please write in the chat box. Dr. Yatendra will compile all your questions and will put the questions to the respective speakers. So now it's my proud privilege to introduce Dr. Jargan. Most of us have been part of his earlier workshop also that was held in Dyal Singh College. He had been vice president of science education in wave function, and he has been scientist and co-director there since 1998. He did his, he had been assistant professor in University of Michigan, research scientist in College of Pharmacy, and he worked in Bell Laboratories as well. And he had the experience of working in University of Texas as postdoctoral fellow. And he had his education, MS and PhD from RWTH, Aachen University, German. And he had been a fellow in the University of Texas and Clausthal University of Technology, Germany. And he had authorship of this Odyssey Molecular Explorer, the computational modeling for chemistry education. And he released its version 2004 and 2018 recently. And he had many publications, to be named 31 publications in physical chemistry, QSAR, material science, and chemical education, and more than 2,500 citations for his work. And we are extremely privileged to have you here, sir.